I'm going to be talking today about Python and Google BigQuery. I am Jeff Kramer. There is my GitHub URL. There is my Twitter thing if you want to tweet at me. My day job, I lead the data engineering team at Vox Media. You may know us from such sites as Vox.com and The Verge and Eater and SB Nation. Hobby-wise, I like to collect late 80s to early 2000s Mac, Silicon Graphics, and Next machines. And this presentation is up on GitHub if you want to go grab it, including the slides and the code that I'm going to run. So first, I'm going to talk about what big data is. So big data is essentially just the new 2010 version of the data warehouse. The data warehouse has been around forever. When I was at Whole Foods Market in the late 90s, we had a 64-node Pentium 2 data general machine that was the data warehouse. Now that would probably live in the cloud or somewhere. If it was physical hardware, it would be like $1 million. So big data is really about time, not about space. So you need 64 processors because these jobs are too heavy to execute on one core. So you need to be able to distribute the workloads across a lot of machines. And it's really hard to do this well. You have to make compromises. There's no solution that you can run on one core that will solve all the problems. And BigQuery solves these really well for data archiving and analytics tasks, which is what we're going to talk about today. So what is BigQuery? BigQuery is Google Cloud's SQL-oriented distributed database system. So it's not an online transaction database. You don't run your ATMs off of it or your e-commerce platform off of it, but it is an online analytics platform. So you throw lots of activity at it, and then you can run SQL on top of it that gives you back insights across a big lake of data. You don't pay anything up front. You don't pay per machine. You pay per query, and you pay to store the data. So you can throw a bunch of data in there. If you never query it, it's really cheap. Once you query it, you only pay for that query. Under the hood, it uses Google's capacitor file format, which I think they have a white paper about. Basically, you give them your data. They divide it up into chunks. They look at every chunk, and they run some machine learning algorithms against it and figure out the most efficient way to store it for querying. And then they store some metadata about it elsewhere. And they distribute it across a bunch of machines so that your query can then be compiled and run across a bunch of machines. And it is fast at scale. There is a video where one of the Google folks does a demo. They have a public data set that has 10 billion rows of Wikipedia access logs, and they do a select group by where title of Wikipedia article includes the term David. And it runs across 3.6 terabytes of information in about 36 seconds. So it's pretty fast. That query costs 20 bucks, which is a lot for a query, but it's also less than $1 million for a new data general system. You load data into BigQuery through HTTP and bulk load jobs, which we'll get to in a second. So if you look at it, if you just load it up and look at it, it looks like a normal SQL database. It supports SQL 2011. It has all the standard types that you might expect from a database, but it also has a struct type. And it uses structs to support nested and repeating data inside of a row. So the screenshot on the right is a screenshot of the UI where they actually show you what the table looks like. And you can see that payload is a record. Record is also another term for struct. And it is nested inside the row. So you can kind of create a document model inside the row if you want. It doesn't have to be flat. And then we have this metadata thing, which is also a record, but you'll note that it is repeated, which means that you can throw multiple keys and values into the same row. So you can have a row that essentially includes like a JSON document as long as it's only one level deep. They have two versions of SQL that you can use to query the thing. The syntax varies slightly. They had a version that was just for BigQuery. BigQuery's been used internally to Google for a long time. And then they have a new version that's SQL 2011 compliant. You can run JavaScript user-defined functions on your queries. So for each row, or when you pull data out, you can actually execute JavaScript against it inside the service, which is pretty cool. The way that Google organizes stuff inside the Google Cloud, you have projects. Projects include data sets. Data sets include tables. Okay, and we're going to actually do some of this interactively. So the Python libraries they try to be fairly Pythonic. They're a little weird, but fortunately I've spent the time digging through the various versions to create a file which has all of these functions in it that works today with the cloud platform libraries. So this is how you create a data set. You create, you get a client, then you create a new data set, you set some fields on it, and then you call the client to create the data set. And once you have a data set, you probably want to create a table in it. To create a table, you need to define a schema. This is kind of tricky with the repeating and nested stuff that BigQuery supports. So this is how you create that table that I showed earlier. So some of this stuff is pretty standard, like there's an integer, here's a timestamp. But then you get into structs, which have fields included in them. In fields, you give it a list of other fields, and then you can have mode repeated fields, which include other fields. And we'll write some data to that in a second, and hopefully it will make sense. And then you create the table, pretty much the same way you created a data set, except you ask the data set, please create me a table. So this is what the Google Cloud Platform UI looks like. Here is the BigQuery part. I created a project called PyTexas BigQuery. It is empty. There are no data sets in it at the moment. I will prove it to you by reloading the page. Okay. So now let's create a data set. Okay, we created a data set, and let's create a table. And if you're looking at the GitHub repo, inside the BigQuery complex examples script, you can see the code blocks for all of the stuff that it's running. So now if we switch back over to Firefox and we reload, we see a complex data set and a complex stream table. And here is the schema. Okay, back to the presentation. So there are two ways to load data into BigQuery. Well, directly into BigQuery that you might, as a client, do if you're not using some other fancy service. So you can load data via HTTP post. And this is their streaming ingestion. So you might want to do this if you have a system that generates log files and you want to throw the log files into something that isn't Splunk or isn't something else, but maybe you want to store them in some SQL queryable data store for a long time that is cheap. So basically what you do is you define a list of dictionaries. So this maps onto the structure that we defined before. So we have visit ID, visit, and then we have a payload, which is nested inside of it. And then here's how we define our repeating columns. So we have key, value, key, value, key, value, key, value. And then we just run this handy little create rows function with our list of rows. Okay, so now we have 3 rows in the system. Streaming data comes into BigQuery a little differently. So I talked about how BigQuery stores things in big files and distributes them across a bunch of machines. So when you send in 3 rows, that's not very efficient to store in a big file distributed across a bunch of machines. So they store it in a streaming buffer until a certain amount of time has elapsed or you've given them enough data. So if we go over to the UI and we hit reload, and we look at this table and the details on it, we'll see there's nothing in it yet. But if we go to the bottom, hopefully at some point, we will see there is now a streaming buffer for it. It won't list anything in there. Small amounts of stuff looked at immediately doesn't show up in the UI necessarily very well, but we can go ahead and query it. So do query data repeated. I will try and put this all on the screen at once. Okay, so this is how we query it. So we use subselects inside of our BigQuery SQL statement. So we select visit ID, visit time, visit location for nested stuff. But then if we want something from that repeating table, we actually use a subselect. So we select a value from a nest where key is first name. And then in the from statement, where you might usually do just a table name, in BigQuery you have to do project name dot dataset name dot table name, because you can talk to other tables and join against other tables. And then you ask the service to pull it out for you. So that's cool. What if we want to translate this data inside of the service before we get it? What if we want to run a UDF on it? You create a temporary function. All functions in BigQuery are temporary. So here we say we're creating a rot13 function. It will return a string. It takes a string as an input. The only language supported right now is JavaScript, and then we just include our JavaScript. This is not a JavaScript conference. I don't really know what that does. I copied it from Stack Overflow. But it rot13s. And you can see down here, we use that rot13 function on the value of first name. And then we run it again. So let's try with the UDF. Okay. And now we have incomprehensible names. Okay. The flow of this presentation is a little funky. Load file. Because I'm doing a load job right now. So we had 3 lines in the table before. That is not big data. So there is a function in this script that will create a 100,000 line random JSON file and then gzip it for you. You can post that file to BigQuery and say import this. That is generally not how you're going to import most data, but it does support that function. I think under the covers they probably store in Google Cloud Storage and then create a load job for you, but it is an easy way to get data into the system. So we're going to do that. And now we're going to reload it. And now if we look at it and we look at the details, we see we have a 17 meg table with 100,000 rows in it. So it appeared. There's a handy preview function in the UI, so you can actually see what the rows look like. So here's what our repeating rows look like. Cool. Back to the presentation. Okay, so let's say that you let your business intelligence folks or your data science folks loose on this. You have a bunch of data in there. So they're going to run a query. That query needs to get back to them somehow. Usually the way you do this is you query into another table. So here's a query. We're going to unnest some stuff. This is the same query as before, but we're going to say our destination for this query is another table, a destination table. And we're going to write truncate. So we're going to overwrite whatever's in that table with the results of this query. And then we create a query job. Each job has its own unique identifier, so we create one of those. And then we start it, and there's a done function on query jobs that you can pull, and it basically will return false until the query job is finished or errors out. So let's do that. So that is query into table. Okay. When the query is done, BigQuery will return a bunch of information in a JSON document to you. Some of those things are things like how much it cost and how much data was processed. Because you are processing data when you make queries, this is useful to keep track of, so you know who caused the bill to go to $1,000 or $10,000 a month. And now, if we reload our data set, we have an output table that is significantly smaller, still has 100,000 rows in it, but the data has essentially been flattened because we ran our SQL statement on it that flattened it out into just a standard sort of SQL statement. So that's querying into a table. Once you have a table, you can export that table out of BigQuery into Google Cloud Storage, and only Google Cloud Storage. There are a couple of output formats that you can choose from. You can output as a CSV. You can't output nested fields into a CSV, obviously. There is a as JSON function. So you can say, like, this nested thing, just turn it into a JSON string and stick it in my CSV, which is pretty handy. You can output JSON files, new line delimited JSON files, and Avro files. Avro is a common big data interchange format. The limit on the file sizes is 1 gig. But if you create your sort of bucket path name with an asterisk in it, it will replace that asterisk with numbering of files, and it will create as many as it needs to. So we create a configuration for our extract jobs. They're called extract jobs. And then we create one, and we run it, and we wait for it to finish. Here is our PyTexas BigQuery bucket in Google Cloud Storage. It doesn't have anything in it yet. We are going to extract table to bucket PyTexas BigQuery. This stuff down here, this JSON, well, it is sent as JSON. This is what gets posted to the API. I printed it on this one just sort of to show what it looks like. So there's a configuration object inside of it, a job reference, and it gets posted to a Google API endpoint. Okay, so we created one file. Let's go look for it. Okay, there it is, 3.2 meg. It can gzip, JSON, and CSV files as well. I think Avro files are like natively compressed. So let's say you have a ton of data and you want to get it into BigQuery. So you're probably not going to stream it because you actually have to pay 5 cents a gig to stream stuff in. You're not going to post it from your machine. You're probably going to have some process that pushes it. So the most efficient way to do that is to copy the data into Google Cloud Storage and then fire off one or a bunch of load jobs on it. We migrated our 700 gig Elasticsearch cluster over to BigQuery. One of the people on my team wrote some Golang code that basically runs Elasticsearch queries, writes the JSON output into a format that we like, and then uploads it to Google Cloud Storage and kicks off a load job. It worked remarkably well. So let's load. BigQuery does time partitions data natively. Is one of the main uses for it. Am I louder now? Okay. Well, hopefully you heard me, and you weren't just nodding your heads in the back to be polite. So it supports day-based partitioning native to the service. And you can write data in to a specific date partition using this decorator. So you use table name, $, day that you want to write stuff into. You have to, when you create the table, you have to define the time partitioning. The only option is day, but you have to set it for it to create that. And then you tell it where to load the file from, and you run a load job. So now if we go back to BigQuery, we have another table, which is our load job table. The underscore partition time field is a pseudo column, and it relates to that day that you loaded stuff in on. If you stream content in, if you stream stuff in to a partition table, this is set to current day in UTC. So if you have some other time zone thing, you're going to have to load stuff into a specific partition some other way. So, yeah. So you can, when you make a request, when you make a query against a partition table, you can limit the partitions it actually looks at. Because that's, whenever you're trying to do cost optimization on a query, you want to limit the amount of data that looks at it as much as possible. And this is how you do that. So where partition time between a certain timestamp and another timestamp. You can also have partition expiration. So let's say I want to throw a bunch of data at BigQuery, but I don't really need to keep it more than 90 days. So you can set a partition expiration in milliseconds, and Google Cloud will automatically delete those partitions when they reach that expiration point. So why would you use BigQuery? It is very low maintenance. It just works. The guy in my team who is kind of our data infrastructure lead used to work at Living Social. He managed a big Hive Hadoop fleet there on physical hardware. He found BigQuery and he was like, this is magic. It just works. It's fast. We don't have to worry about it. We don't have to get pages in the middle of the night. Also, you pay on demand. So if you don't use it a lot, you can store the data there. It's 2 cents a gig for storage. If it's been touched in the last 90 days, if you haven't touched it in the 90 days, most recent, it drops to a penny a gig. So that's pretty cheap. So there's easy connectivity to other Google products. If you have a really high level of the Google Analytics data suite, if your company is paying for expensive stuff, they will give you your raw data in Google Analytics in BigQuery. YouTube is working on the same thing. It's kind of buggy right now. Google's Data Studio has easy connectors into this if you want to do business intelligence and data visualization stuff. Google's Cloud Data Flow, which is Apache Beam under the covers, I believe, lets you set up connections between things where data gets routed into specific places. And you can export stuff into Google Sheets really easily. So you can run a SQL query, and there is a button in the UI. I think I made it too small. Okay, here it is. Query history. No. My UI is too small. Okay. You run a query. Oh, invalid table name. Okay. You run a query, and there's a button in the UI that says export to Google Sheets, which is pretty handy. Why wouldn't you use it? Don't use it for application style workloads. Don't use it for like all the users hitting your service, your website, because it is not super fast on the interactivity scale. Just use Postgres or something for that. Don't use it for transactions. Obviously, it's not designed for that. It is eventually consistent. If you're in AWS, you're not going to use it, probably. If you're on premises, you're probably going to want something else, like Apache Impala, which is kind of the Apache project's version of this, based on the white paper. If you need to do a lot of updating of your data, this probably isn't for you. It is really a write-once service. They do support 100 update and deletes per table per day, but that's it. So if you have GDPR or EU privacy stuff that you have to do, where you have to clean stuff out of your data set, you can do that as long as you don't have more than 100 people a day asking you to do it. And that's it. Questions?
How easy was the transition from Elasticsearch to working with BigQuery?
Easy.
It was really easy.
Yeah. I personally don't like querying Elasticsearch. Like, no, I don't like JSON queries. I don't like defining my queries in terms of like JSON nested if and greater than statements. I like SQL. Yeah.
Myself wanting to run a gigabyte table, right? So there's not the equivalent of like database table. So is there a way to like
So you can use other partitioning schemes. Oh, sorry. Is there a way, so BigQuery and other big data solutions don't do indexes, because indexes are essentially just small tables that only include the columns you care about, which doesn't make sense when you can scan something distributed across a bunch of machines. So how do you limit your cost and performance if you only want one specific thing inside of your data set? So if your table is really big, if you have a row and there is a ton of data in it, you can partition your tables through other methods. BigQuery has alpha features where you tell it which column you want to partition on, if you want to use something other than the pseudo time one. The Google Analytics data that we get, because it's built on an older style of BigQuery, it actually uses a different partitioning scheme where instead of using the decorator model, it uses underscore date. But other than dividing your data into smaller chunks, not really. Anything else? Cool. Thanks, everybody. Oh.
So you kind of dug at the Python API a little bit.
Mm-hmm.
Is it good? Is it bad? People wrap it?
So Google has like a raw one that their CLI uses, where you basically have to construct your query yourself, and then you use the functions to send it back and forth to Google. This one is the most Pythonic, in which, insofar as you don't have to worry about how that stuff works, you can overwrite things into it. It used to be harder to like insert an element into the JSON for an alpha feature that isn't supported in the API wrapper yet. It lags a little bit. So if you're using established functionality, it's good. If you're trying to experiment with like the alpha stuff, or you get into a beta, it's a little trickier. But I mean, it's generally fairly good. The problem that BigQuery has is the documentation points to lots of different versions of API wrappers. So figuring out which is the most supported one and the one you should use can be a little tricky. So, cool. Thanks, everybody.